Eighth graders, today's assignment is day 2 of the temperature plateau, and of course this is day 2 of our phase change engineering internship. If you guys haven't finished day 1, make sure you guys go back and complete day 1 first, because when we talk about the PCMs, it's really important that you guys have a good foundation about those PCMs before you guys talk about the temperature plateau today, because this is going to be kind of digging more into how those PCMs work. So again, make sure you guys finish up day 1 before you guys start this assignment today. Okay, with that being said, your guys' learning targets, I can describe the changes in temperature and kinetic energy when a substance melts or freezes, and then I can explain what happens to kinetic energy and temperature during a temperature plateau. So one of the things I kind of want to touch on that we talked about yesterday was the concepts of freezing. I asked a couple of my classes, when you hear the word freezing, what do you think of? What are some words that come to your mind? And a lot of kids said cold, ice, chilly, whatever the case is. But I want to kind of bust that misconception up, because not all phase changes from liquid to a solid are going to be something that are cold, okay? And you guys saw some examples of that again in the lab yesterday when that little PCM froze, but it also got way hotter because it was releasing energy. Okay, so something for you guys to think about. And then your next learning target, I can explain what happens to kinetic energy and temperature during a temperature plateau. So that's going to be a really big concept that we're going to hit on a lot today. Okay, for you guys' bell ringer, you guys have a little reading to do. So read chapter 3, the temperature plateau. You guys open it up. You guys might need to click on your table of contents up here and go to chapter 3, temperature plateau. So do a really good job reading through that. We're going to really dig into these temperature graphs for for freezing and for melting, and talk about what's happening during this temperature plateau. So really, like I said, really make sure that you guys do a good job reading that. For your question you need to answer for this article, remember, energy cannot be created or destroyed. Even though thermal energy is being transferred in, when a PCM is changing phase, its temperature and kinetic energy remains the same. What happens to that thermal energy that is still being transferred in? So obviously, if we're causing something to melt, we're heating it up and we're adding energy to it. So if that temperature stays the same, okay, that means the energy is staying the same as well. Okay, so what happens to that energy that we're still adding in it if we're heating it? Like if, well, for instance, we're using a Bunsen burner like you guys see in this picture here. Okay, that's found in that article there. So again, take a second, pause this video, do a good job reading, and answer the question on slide 3. When you're done, we'll come back and talk about the next little video. Okay, for the next part, you guys are going to watch this video, the temperature of melting ice. You guys don't necessarily need to watch the whole video. At the beginning of this video, it kind of asks you guys a question. So this is an experiment to find out what's hotter. So if we look at ice that's just starting to melt or ice that's almost melted, which one has a higher temperature? I don't like the fact that they use the word hotter. So which one has a higher temperature? So you guys can kind of see where this experiment starts out as far as temperature. Obviously, we know that water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. Okay, so as that water is going from solid to liquid, okay, at what point is our temperature hotter? So go ahead and take a look at that, and then just let me know what you guys observe. Okay, and once you guys are done, come on back to the main video. All right, so what you guys should have seen with that is that whole time that ice is melting, the temperature remains the same. So when we're looking at, all right, this ice is just starting to melt, or this ice is almost completely melted, it's the same temperature, and that's what we call the temperature plateau. So it's a period in which there's no change in the kinetic energy or temperature of a substance as it undergoes a phase change. So while that ice is melting, there's no change in the temperature, no change in the kinetic energy, even though we're putting heat into it to melt it, whether that heat's just coming from our surrounding or if it's coming from some kind of heat source. So even though energy is being added or removed. Okay, so we're going to take a look. There's actually 2 temperature plateaus that you guys will see in this little graph on slide 6. So we can see that we're removing the thermal energy, the temperature of our substance is dropping, and then it gets to the freezing point. We don't have actual numbers here to demonstrate what the freezing point is, but while that substance is in the process of freezing and moving from a liquid to a solid, that temperature is going to remain the same over time. Okay, once that whole substance is frozen, as long as we're still removing energy, the temperature is going to continue to decrease after that. So once it's completely frozen, then our temperature will continue to decrease. Okay, likewise, you guys can see this yellow or this pink bar at the top. That's our heating. So if we start transferring energy in, heating that substance up, we can see our temperature rising. And once it gets to the point, the melting point, we're going to see that the temperature and the kinetic energy is going to stay exactly the same for however long it takes to melt. Okay, so the melting, there's our temperature plateau right there. And then once it's completely melted, as long as we're still putting the same amount of heat into it, we can see that the temperature is going to start increasing again. So these two represent a freezing temperature plateau and a melting temperature plateau. And you guys can kind of notice that they're both about the same temperature because we're at the same phase, right? We're either going from solid to liquid or liquid back to solid. Okay, so that should occur around the same temperature. Okay. All right, so what you guys are going to do on this next part is you're going to take a look at some phase change graphs. Basically, we're going to look at what we just broke down in this one here, except you guys are going to split them into two. So we're going to look at one first and then the other. So use the text phase change from solid to liquid to annotate the phase change graph. So we're going from solid to liquid. That would be a melting temperature plateau or a melting phase change graph. Use the focus questions below to help you annotate. So you guys will see this in two pictures or in two slides on slide 9. These same questions will be repeated, and that'll help you guys kind of annotate your graph. So what happens to energy and temperature when the PCM is solid? So you guys will kind of point out when the graph is solid or represents a solid, when it's melting, in the process of melting, and then when that substance is now a liquid, you guys will kind of identify what's happening to the energy and temperature of that PCM. Okay, and then finally, what's happening in that temperature plateau. So first thing you guys want to read is this little blurb on slide 8, phase change from solid to liquid. PCMs like these are solid at room temperature. Boiling water transfers thermal energy to the PCM, heating it up and increasing its kinetic energy and temperature. When the PCM begins to melt, so that's going to kind of mark the start of our temperature plateau, changing phase from solid to liquid, its temperature stops increasing for a while. So again, that's where you guys see the flat line on the graph. This is a temperature plateau represented by the flat part of the heating phase change graph below. Even though thermal energy continues to transfer in, the kinetic energy and temperature of the PCM remain constant. Instead of increasing the kinetic energy of the PCM, the added thermal energy is converted to potential energy and stored in the PCM when the freedom of movement of the PCM molecules increases. So this is basically kind of going back to one of our learning targets and our bell ringer. What happens if we're still heating something up to cause it to melt, but our temperature and our kinetic energy are staying the same? What's happening to all that energy that we're still putting into it when we're heating it up? Okay, the answer is that it's going to be stored as potential energy in that PCM, and that's why these PCMs would be so great to use as a little incubator for a baby, is because of that stored energy and because of this temperature plateau, we're going to see some of these PCMs are going to be able to store a lot more energy than others, and we might see that that's going to cause them to last longer as an insulating factor or a heating factor to one of our incubators. Okay, so instead of increasing the kinetic energy of the PCM, the added thermal energy is converted to potential energy and stored in the PCM when the freedom of movement of the PCM's molecules increases. The plateau is complete once all of the PCM has melted. Its temperature and kinetic energy begin increasing again, so it's stored up a lot, and now the temperature can start going up a little bit more. But again, it's still stored. Can begin increasing again as the boiling water continues transferring thermal energy to the PCM. So then as we use that heated up PCM in our baby incubator, because of all that extra stored energy, we're going to see it maintain heat a little bit longer, be able to transfer its heat a little bit more to that baby in its little sleeping bag. Okay, so this is what this would look like. And you guys can see those same questions that I pointed out earlier to you. Okay, here's a heating a PCM or melting a PCM temperature plateau. So these are the questions you guys are answering. You guys can see where I highlighted the solid. What's happening to the energy or the temperature of the PCM? So at this phase right here, the temperature is going up and it's still solid. Okay, so you guys would talk about how the temperature and the energy is going up. You guys don't have to do complete sentences. I'd be happy with something like KE, kinetic energy, is increasing. Temp is increasing. So you guys can keep it pretty simple, okay? If we look at the liquid phase of this, notice how the temperature is still rising here. So that also means that the KE, the kinetic energy, and temp are increasing still. Okay, and then in the process of its melting, what's happening to the kinetic energy or the temperature here? So you would say the KE, the temp are both staying the same. So they're staying the same. Okay, so you guys can keep it fairly simple. Okay, the big one though is what is the temperature plateau? So kind of describe to me what's happening with that temperature plateau. And again, we just talked about that. It's kind of this whole little section right in here where we're talking about the potential energy and storing energy. Okay, so you're going to describe how that potential energy is kind of useful for that PCM. So go ahead, answer that question there. Okay, you guys are going to do the same thing for the freezing model. So as our PCM cools back down and turns back into a solid, you guys will answer those same questions, okay, like you did on the last chart. So make sure you guys fill out slide 9. Don't forget to do the temperature plateau. Okay, and then you guys will do the reading again. You'll learn about how this energy is going to work. It's not going to be the same as storing it because in this case, remember, we're losing energy. So make sure you guys do a good job reading through that and seeing what happens. And then in this case, you guys can see, all right, it was a liquid. We heated it up. We used it, but now it's transferring its energy to the baby. So it's going to start losing its energy and cooling down. So what's happening when it's a liquid as far as energy and temperature? Same with solid after that turns into a solid and freezes, what's happening to our energy and our temperature. What's happening in the freezing, and then what's to the energy and the kinetic energy and the temperature, and then talk about how this plays in with the temperature plateau. Again, you guys really need to read through this here where it says during the plateau. Okay, so make sure you guys understand where that stored energy is being used that we talked about on the last graph. Okay, so make sure you guys complete this one this one as well. Okay, so you need to do all 4 of these. Again, I haven't helped you guys on those ones. Okay, well, go ahead, take a second, pause this video, and when you're done, we'll come back and go on to the next part. Okay, this is where we get introduced to the actual design tool where you guys will be designing these incubators. So go ahead, take a second to watch this video. It looks like this. It's going to just explain to you guys how this modeling tool works and a little bit of the things you need to know about it. Okay, and when you're done, you guys will kind of take a second to open up the sim that you'll be using to collect data for the rest of this unit. This is your baby warmer sim. So you guys will go ahead and set up this example and kind of see what happens and what you're looking at. So open the baby warmer design tool. Take a few minutes to explore if you'd like. Reset your data. Choose only 2 PCMAs and 2 PCMBs. So I'm going to go ahead and choose PCMA. I want 2, so I'm going to add 1, 2. And you guys can see how they kind of fit in their little pockets. And then PCMB, 1, 2. Okay. And then what you guys are going to do is test your design. Once you guys hit test, you're going to unclick or unselect the baby line on the graph. So you guys are just looking at what happens to the temperature lines of the 2 PCMs. So I'm going to go ahead and hit test. And then I don't want to have too complicated of a graph. And you guys can even look and say, all right, here's just PCMB. Okay, here's PCMA. So you guys can kind of see how those different PCMs have different temperatures, those kinds of things. They have different lengths of time for their plateaus. So I want to point out the questions that you guys are going to answer based off of this information that you see on the graph. So answer the following questions. What type of phase change is occurring? So you guys are seeing, all right, here's the PCMA, temperature's falling, then it's plateauing, and then it's falling. And then we see it back up here, it's falling, plateauing, falling. In the time in between, so if I click and drag right to the end of where this purple line drops off to the next one, that would be where we would take the PCM out of the little insulating vest for the baby and heat it back up. Okay, so it would have turned to a solid. We need to reheat it, so we would boil it. So if you guys look up here, here's a little image of boiling water, and you guys can see the little purple bars that show you guys, all right, from this point, again, if you're looking at the top right here, okay, from this point to this point, that's where we're boiling. And then we would stick those back in. So at this point, that's where we stuck the PCMs back into the vest and watch the energy transfer into the baby. Okay, So just some things I wanted to point out for you guys. What type of phase change is occurring? So this is for both A and B. You guys can see the same phase change reoccurring over and over on this graph. Okay. How can you tell that a phase change is occurring? So make sure you explain how you can tell that you have a phase change occurring. How do you know? Okay. For each PCM A and B, what is happening during the temperature plateau? Use the term potential energy in your example. So again, think back to those two graphs that you guys just analyzed. On one, you're storing potential energy, and on the other one, you're using that stored potential energy. So how does this apply to these graphs that you see right here? Which one kind of matches your answers? Okay, so this one potential, here's your temperature plateaus for A. Here's your mini temperature plateaus for B. Okay, so that's definitely going to be something that you guys need to consider there. Next one. What is the temperature of the plateau for A? So you guys are going to look and say, all right, basically what's our freezing and melting point for the PCM-A? You guys can kind of look at it here. And if you guys drag it back where it's just looking, you guys can kind of see the temperature as well. So if I look at it where it's just the purple one, I can kind of see where my temperature is right there. It looks like it's about 36.9. Okay. Same thing for B. What's the temperature plateau for B? And then how long does the temperature plateau for A last? So this is measured in seconds, or excuse me, minutes. So you guys can kind of start and say, all right, here's the time at 325 minutes. Here's my time to 563 minutes. What's the difference in that? So you guys can kind of get an exact time by clicking and dragging the blue circle back and forth. Okay. So answer those questions about each temperature plateau. And then why is there spaces or breaks in each of the temperature lines? So when I refer to that, I'm talking about like these spaces and breaks right here if I'm looking at the orange ones, or these big ones for the purple. Okay, I've already explained what's happening there, so think about that. And then which PCM takes longer to heat? So when we have to reboil that to turn it back into a liquid, okay, which one takes a longer time to get it back into a liquid? Okay, and then finally, RN, how do you know? So make sure you kind of explain what part of the graph kind of tells you how you know. And then finally, the last question, there will be a lot of other factors to our design that we will consider as we work through this project, but just based off what you guys looked at with PCM-A and PCM-B, which do you think might be a better fit for the baby warmer? Remember that your goals are to keep the cost low, to keep the baby as close to 37 as possible, and to kind of minimize the amount of time it spends above or below 37 degrees. Okay, so you guys would circle PCM-A, PCM-B, and then tell me why. Use some data from your experiment. This will be good foundation for what you guys are going to continue doing on day 3 and day 4 when you guys start designing the whole comprehensive baby warmer. Okay, once you guys are done with that, go ahead, do your exit ticket. Any questions, yes or no? If yes, type them below, and then 4, 3, 2, 1, how do you guys think you did? Again, remember, you're kind of setting the stage right now for you guys to try to get your proposal selected by me as the company head, and potentially win some caramel cookies. So make sure you guys are paying attention and working hard now, because it'll make your time easier later. Great work. Make sure you hand it in, and I'll talk to you later. Bye.